Hello. In this video we're going to look at an application of the graphs of trigonometric functions. So specifically we're going to look at blood pressure. So we're going to see a graph, but the graph gives the variation in blood pressure for a typical person. Systolic and diastolic pressures are the upper and lower limits of the periodic changes in pressure that produce the pulse. The length of time between peaks is the period of the pulse. That's basically, so let me show you the graph here. So basically they're saying here, it's not exactly, of course, smooth like we normally see a sine or cosine wave, but it's somewhat approximated, right? So this looks to me like a reflected cosine with, this part, the first part, being very much like a cosine wave, but then as it comes down, the slope is a lot more gentle. So, we're going to just approximate it with a graph, with an equation. All right, so they want us to find the systolic and diastolic pressures, which are the upper and lower pressures. So we should be able to just look at the graph actually and just see, okay, the highest pressure is 120, the lowest pressure is 80. So your systolic pressure is 120, your diastolic is 80. Find the amplitude of the graph, the pulse rate, and then I added, let's go ahead and find the equation of the graph. All right, so as we mentioned then, here's the max, here's the min, right? So the systolic pressure is the max, which is 120. All right, and the diastolic is basically the min, which is 80. Right. Now that's part A. Part B, find the amplitude. Right. So what we see is we go from 80 to 120, and what would be in the middle? Well, if we take an average 120 plus 80 and divide it by 2, we'll get 200 divided by 2 is 100, right? So basically 100, it would be the new x-axis. And so what are we going from? Well, from 100 to 120 is 20, or from 100 to 80 is also 20, it's just negative. But so basically the absolute value of the amplitude is 20. All right, but it's a reflected cosine, right? Because it starts at a min. So we know that A itself is going to be negative 20, right? Because it looks like this, right? Where that's a reflected cosine. Okay. And then, so that was A and B, find the amplitude. C, find the pulse rate, the number of beats in 1 minute. So what they're showing us is this isn't exact. So here the divisions aren't fantastic. But basically, here's one wave from this max to this max, and it's 0.8 seconds. Okay, so what you see though, the way they've divided this is here's 1, 2, 3, and then notice here this is a little bit beyond 3. So the divisions aren't what I would have chosen, but hey, what can you do? All right, so what we know is that if we're going to find the pulse rate, the number of beats in 1 minute, and this is being measured in seconds, then I want to change 1 minute into seconds, so there's 60 seconds in 1 minute. So how many beats will I have in 60 seconds when each beat is 0.8 seconds? So 1 minute equals 60 seconds. And then I want to know how many sets of 0.8 seconds are there in 60 seconds, right? If you divide that out, you'll get 75 beats. So that's basically 75 beats per minute. Now the last part of this I'm adding to what was the book's problem, and I want to just find an equation of the graph, and it's going to be approximate, right? It's not going to be exact, because really my cosine wave should probably go something like here, right? And then it would start coming down here, right? And so it's a little off, but it's still pretty impressive that we can somewhat approximate it. So let's go ahead and do that. So I want to go ahead and say, okay, let's find the equation of that graph. So I already know, right, that A is negative 20, right? Oops, don't know what that was. And that we know the period is 0.8 seconds, right? By the way, here we also know that K was 100, right? So we found the new x-axis to be y equals 100, or in this case, whatever the P, the pressure, is 100. Okay. And then we want to use this here to find B. We know that 2 pi is the normal amount of distance it takes to see a cosine wave, so we're going to divide that by 0.8. Now what I would do here is just go ahead and do 2 pi divided by 4/5. So let me just kind of put this here to the as an aside. So we have 0.8 is 8 out of 10, right? Which when you reduce is 4/5. Okay, so that's where we're getting that. So I'm going to do 2 pi over 1 divided by 4/5, which is 2 pi over 1 times 5/4, okay, which is 10 pi over 4, which of course you will then reduce to 5/2, right? Okay, so that's B. So we now have, and then C, we know starts at 0, right? There is no phase shift. It is 0 because you're already at the min. All right, so C is 0. Or you could do this, negative C over B is 0. And then no matter what you put in here, you're still going to get C equals 0. Okay. So now the equation I would get would be blood pressure would equal negative 20 cosine of 5 pi over 2t. And that would be it. So if you wanted to, you could add plus 0, oh sorry, plus 100, right? So there's no C. So this would be my equation. It's just approximate, right? Because we said it's not exact, right? We're not going to get it exact. Well, let's go ahead then and put this in the calculator and just see what the graph of this would look like. All right, so I would be in radian mode. All right, so make sure you're in radian mode. And then I've already got that put in for us. And the windows that I would use are probably, if you look here, since each wave is about 0.8 seconds, and they've got 1, 2, 3, 4, 5 waves, you do 5 times 8 is 40, so 4 seconds would give us quite a few waves. That would be pretty good. So I'm going to go from 0 to 4, and I'm doing the scale as 0.8, so I get each wave. And then remember, our amplitude was 20, and then we went from 80 to 120. So I want to go a little bit below and a little bit beyond that. So I went from 7 to 130, and I just decided to split that scale using 10. Now if I press graph, there you go. And you can trace this, and you can see things like, okay, where is the max? And it looks like at about 0.42 seconds, you're almost at 120 for your systolic pressure. Then you can see how, where is it probably about 100. It's at about 0.61 seconds, and so on and so forth. Okay. All right. Thanks so much for listening.